All right, so let's just come up with an algorithm here. All right, what's the algorithm? Is the input is a sentence, right, and a model, right? And we want to decide whether it's true or not, right? And of course, if you've been reading up on Gödel, you know that this is impossible, right? But we're going to do it anyway, right? We're going to have a kind of an infinite algorithm, right? All right. So where are the problems in doing this? It kind of says why it's hard, right? And if I'm trying to prove that there exists some y, right, then the hard part is I have to construct this y, right? And it may be very hard for me to construct, right? So if I want to find a sequence of zeros and ones that satisfies a circuit, right, there are 2 to the end of them, and I have to search all of them. So it takes me exponential time, right? If I want to find a sequence of integers that satisfies some equation, how many integers are there, right? There are an infinite number of integers. So I have to try them all, right? Right? I want to know, for example, does there exist a time at which my Turing machine halts, right? You might not have taken 2001 yet, but the halting problem is undecidable. You give me a Turing machine, and I want to know, does there exist a time in which it halts? Well, one way to prove that is you try all various times, right? You run it. Does it halt in 2 steps, 3 steps, 4 steps, right? And they're an infinite number. So there is an exponential time algorithm for this, but there are no algorithms for these that run in finite time, right? You have to try all x's. But that being said, you know, in some ways, this is an algorithm for this statement, right? It tries all w, it tries all x, but the problem is there are an infinite number of them, right? So you could say, well, this node right here, right? I plugged in a value for w, I plugged in a value for x, I plugged in a value for y, I plugged in a value for z. So now I can see, is alpha true on those values, right? And so here it's just for each path, we write down whether alpha is true or not, right? And then, well, the OR says, is one of them green, right? Here none of them are green, so we get a red, right? And the AND is we do an AND of them. So are they all green? No, this one's here they're all green, but here they're not, right? And then those values percolate up, right? Everybody see that? Like this is just a circuit turned upside down, right? Everybody say we're just evaluating this thing, and right? And then if the root is labeled green, then it's true, right? And now let's go back to the game, right? Everybody knows that if you're playing chess, they're game trees where I get to make a move and then you get to make a move and I make a move, right? So this is the same thing, right? We're assuming, how do I prove Forall if the adversary comes up with it? How do I prove it exists? I come up with it, right? So as a prover, I'm going to choose the exist, right? And as a Forall, the adversary is going to choose the Foralls, right? We're going to, right? Because if it's an exist, right, then remember the exist was the OR, and so the prover does it, and the Forall is an AND, right? So when do I have a winning strategy to this thing? Well, I have a winning strategy when the leaf is colored green, right? And here's the game, right? I'm sitting here. It's my turn. It's an and. So who gets that? Says everybody down here. If it's an and it's green, that means all the children are green, right? So the adversary gets to decide to come this way. And if it's an or, so our loop invariant, I like loop invariants. If you know what a loop invariant is, it's what's true as we go along. What's true as we go along is that we're sitting on a green node, right? We started on a green node. Then since all our children are green, doesn't matter which way you go, the adversary sends you, will be on a green node, right? And now I'm sitting on a green node, which is an or. That means at least one of the children is green, right? So what do? I say I get to choose which way to go to the green, right? Does that make sense? Follow the green. And then it's the adversary's choice. So it doesn't matter which way the adversary goes, it's always going to be green, right? And then it's an or, so I get to choose which way to go. Everybody get the game? So it's just, again, we've looked at things in different ways, right? We've looked at the game compared to proof by contradiction, the game versus these formal add and remove quantifiers. We're looking at the game compared to this decision tree, right? It's all the same. So any questions about that? All right, so here's just a little example. What's the game? The whole game is white moves. So white specifies the first move, and then black specifies the second move, and white wins if there's an edge between them, right? Everybody get the game? So we want to see who has a winning strategy. And so what we're going to do is we're going to say, right, is it black or is it white? Right? The statement is, I have a winning strategy. White can win. And he's trying to say, no, I have a winning strategy. Black will win. Right? So let's, here's a specific game, right? He goes this move, and black goes that move, and look at black wins, right? So now white goes this move, and black goes that move, and again black wins, right? And we can say, look at all these possibilities, right? Everybody see that? And so what are we saying? We're saying black has a winning strategy, right? Why? For every first move that white goes, right, no matter what white goes, there exists a move that black can go, right? And you'll note that black's move depends on white's move, right? Because that's the way the game works. White goes first, right? All right, everybody get that example? So now I added an extra edge in here. Right, you see that? I just changed the game. And now, what is white going to do? White can come down here. And then no matter what black does, white wins. Right? So what are we saying? We're saying there exists a way for white to go. Right? Here, this is the way. Come up with one. There's one move that white can move that no matter what black does, white wins. Right? People seeing this? And if this is on one of the, I gave you various homeworks, and this is in there, right? So maybe you've seen it already. All right, so the game tree, right? It's a 2-move game. Well, didn't we do this already? Right, here's, right, here, right, white goes, and then black goes, and then white goes, and then black goes. right? And then it says black wins. Everybody good? I know why I've seen this recently. I'm giving an AI talk today, and I looked at this slide just on the subway on the way up here. All right. So what are we saying? We're saying there exists a way for white to go, so that no matter how black goes, there exists a way for white to go, so that no matter how black goes, white wins. Right? Everybody see that? It's a game. And in 2001, they proved that certain languages can't be done by finite state automata. And they do it using a thing called the pumping lemma. And the pumping lemma has 5 levels of alternations. And the students don't really understand the difference between existence, Forall, and form exists. So how the hell are they doing 5 levels of it, right? So when I teach it, I turn it from the pumping lemma to the bumping lemma, so there's only 4 levels of alternations, and we play the game, right? All right, so, right, how do you prove it? White needs to say how they're going to go first, right? And then no matter how black goes, there's a way for white to go, so that no matter how black goes, white will win. Right, everybody get that? And we work backwards, right? Here, this says that white to win needs to end on a star, right? So what do we do here? Well, what's black going to do? Black's going to go to the black if there's a black, right? So the only way we can go, right? If the game is here, then who's going to win? White's going to win, right? Because no matter how black goes, right? So we can mark this as white wins. And then in all of these others, right? Who's going to win in this one? Well, black's going to win, right? And so you can bubble up again and say who wins, right? At each level. People kind of see that? It's again, we're just taking the and the or. Right? And that says we've labeled it as a black, right? So because black can win.